Should we start? Okay. Okay, good morning. Thank you very much for coming to the session today. I'm going to give a progress report on the work we have done on Secure Control Module. I first presented this at March Global Summit. We have done a lot of work towards that. I'd like to present the results. We've been working together with a platform team at Google to formalize the Pinout and make it more useful. In addition to Google, there have been a number of other companies who participated and provided feedback. Feedback is always great. We include good comments and hopefully making the interface more useful. Basically, we're doing this secure control module to make things easier for people, make things more useful, and making an open source hardware might make it easier for people to build systems that are interoperable, making the design of a system just a routine practice of getting the guidelines from the processor or SoC vendor and have the secure control module part of it as a standard so they can interoperate. Once we do that, then it is more likely that the product that people come up with are ready for data center inclusion faster. That's the main reason we're doing all this work. So what is a modular building block architecture? It can start with a combination of four major elements. We have compute element. Along with the compute, we have I/O elements, accelerators, or networking cards. We need management in a secure way. Of course, we need some interconnects to combine all of those. On the control, it could be data plane control or management out-of-band control. This modular building block architecture is built on the notion that we have small elements. Small elements are easier to build, easier to integrate, easier to fit in any configuration. With individual modules, if we have clear definition of input and output, it is more likely that they can be interoperable. In this particular example, we have a solution for I/O slots to be as part of a riser or a cable-connected solution. We're trying to get ready for PCIe Gen 5. So if the modular building block architecture is a catalyst for making things faster, the secure control module can facilitate that. So once we do that, again, designing a very complex system could be a routine practice of doing the best thing that each company or each group does. The processor memory complex could be done in a very good way and tested separately from the rest of the system that make it specific to a particular data center. Some of the examples of modular building block architecture. This is the concept we started last year. We said, well, let's start with a motherboard, but only the essential elements around the processor, which is the processor, memory, and I/O slots. Just keep those, put them separately. As you see, this module is only based on what a processor vendor prescribes. The distance, trace routing, design guidelines for interfacing to the processor. It does not require a full requirement set from the end customer. That can be customized later. And another example is the connector spacing. When we do it this way, the I/O slot connectors can be much closer to the processor. That will help with the trace routing and signal integrity. So PCIe Gen 4 and PCIe Gen 5 might be a little bit simpler doing it this way. Whatever else is left is part of what I call Secure Control Module. So a combination of Secure Control Module and the CPU memory module make what we used to call a motherboard. So you can have Secure Control Module plugged in directly, or we can have a system that can maybe place the Secure Control Module a little farther away. So we started a concept a while back, just some CAD drawings. Our target was a tight coupling of the memory and the processor as usual, tight coupling of I/O close to the processor. And then we picked a suitable connector. The connector in this model is the standard that a lot of industry standard efforts are using, EDSFF, Gen Z. So the interesting thing about this connector is that it can be plugged in a vertical form, right angle form, straddle mount, or even be cabled. So we put this concept to practice. We actually build a system around it. Wewin helped us build a system around a single socket processor and a secure control module as separate elements. For the I/O connector, we needed high-speed cabling between the CPU memory module and the I/O slots. So we had some concepts. We said that we wanted to support a PCIe slot anywhere in the chassis. We came up with two different versions of it. TE and 3M both participated in that discussion. And eventually, 3M produced cables. These are the cable harnesses, if you guys want to play with them. Using the same connector that Gen Z prescribed for the CPU memory module, it's the same connector, not necessarily the pinout, and a PCIe chem slot connector on the other end. This was a good solution. Gen Z connector pinout did not include some signals that we thought were necessary for PCIe slots. For example, it did not include JTAG. So we came up with a pinout for the connector side on the CPU memory module that is very similar to Gen Z, but added whatever else we needed for this to be a useful connector for general purpose PCIe slots. You can read this one later. But from the mechanical point of view, we had some challenges. We needed to make sure the cables fold in a small enough area, and 3M did a very good job with Wewin. They worked together to come up with some design guidelines for these PCIe slot harness. Later, we looked at the signal integrity, and based on that work, we saw that it was nice to have bypass caps, high-frequency bypass caps on the PCB so that we could reduce the signal, simultaneous signal interference. Then, from the mechanical point of view, one of the goals we had was to increase the number of PCIe slots we could have in a 1U space. One of the examples that's going around shows how we actually coupled two of these connectors on top of each other. This is a connector with only one that could be anywhere in the chassis. The other one has two of these coupled together as a 2-slot in a 1U envelope. So other concepts that were possible with this connector family was to use the connector side that's on the motherboard on the CPU memory module positioned in a place that you could plug in either the cable or a riser in a normal position that people use riser cards. So we could either cable a solution to the CPU memory module or plug in a card using riser solution. If we do it through cable, we believe that we can do a closer approximation of PCIe Gen 5. The work is not done on PCIe Gen 5. We have demonstrated it works with PCIe Gen 4. PCIe Gen 5 might have a little bit more work to do, but that's the work in front of us. So again, we realized that solution in a system. We went and 3M did a good job of combining the concepts. We built it, brought it in the lab, ran a lot of tests on them. So when you put them all together, a tight system can be built. Because the modules are small, they can be placed anywhere in the chassis. Different configurations are possible with low profile PCIe cards, half-length PCIe cards, even GPUs, double width, full-length PCIe cards are possible in a 1U chassis. This is just one example that shows we have cable-connected PCIe cards and riser-connected PCIe cards. Configuration, bit rate, cost, serviceability, all those are factors in choosing which one of those are more appropriate. So far I talked about the connection, but let's just talk about the secure control module as well. So the rest of the management needs to be done in a compatible way. For that, we need an interface that's compatible, and we need a module that might be flexible actually, need not be prescribed as fixed, could be flexible as long as we have the interface common. So just imagine you start with a motherboard, you take out the processor, memory, and I/O slots out, put them in a module, call it CPU memory module. Whatever is left out of the motherboard is the heart of the motherboard. And that will include things like BMC, root of trust chip, boot devices, flash devices for BMC, for system, and even a boot device for OS image as an optional feature. Such a module can then control single socket, dual socket, 4-socket systems, maybe even JBOD, expansion chassis with GPUs. It can be built to be flexible. So why did we do all of this? We just didn't want to reinvent the wheel every time that we designed a server. We've done that enough times. It was getting tiring, and took a lot of resources. So we thought that if we focus on one set of data center specific requirements, the processor and memory module can change to accommodate the compute that we needed. By doing that, then we could push for common tools, firmware tools, diagnostic tools, repository tools, so that that could stay the same even if the processor numbers or types would change. And then hardware is not complete without software. Working closely with the software community on standard firmware practices, OpenBMC as an example, EDK2 as an example, is also an essential element. Within the OCP, there are a number of work groups and projects around common firmware, either for BMC or for system firmware, that we can benefit from that work as well. hopefully you're already part of that discussion. So then, recognizing as part of the building blocks, most of the modules within a modular building block architecture are stateless. They don't have firmware on them. That makes them essentially secure. So the security comes from a security chip on the system module, the security control module. It controls all the firmware that's in the system. You have the real-time clock for making sure that the timestamp is the same for all systems. But the form factor itself could be different. It could be cable connected, as I showed. It could be plugged in a very small module similar to NIC3. And it could be of the form of a plug-in card, low-profile PCIe card, for different advantages. Different systems might require that. As long as we have the interface as common, we could be successful. So this is an example. This is a superset example that keeps the interface the same. We are using the 4C plus connector here with 168 pin positions. It includes all of the main ingredients of a system. But we could have a different form factor of the same. A module very similar to NIC3, plugged in from the front, might be suitable for a dual socket server. Whereas a secure control module such as this one with flexible connectors might be good for an expansion chassis, JBODs, larger systems, or for development vehicle. Software teams can use this one. The BMC itself could be different, could be from a number of vendors. Security chip might be different. So we built actually one based on the superset. It is available. WeWin has this one available. Give you some example of the work that we've done so far. It is work in progress. Specification is not complete. We expect to complete the specification based on the feedback we're getting from you and the community by March, Global Summit March. It will include detailed block diagrams, connector selections for it to be useful for others. This is an example of an expander connector. This module can control things outside of the CPU and memory module. The number of fans, as many fans as you need in a system, temperature sensors, debug. On the Pinout took a very long time for us to consolidate. Feedback came from many companies. We put them all together in a very large spreadsheet. And even names were different. Same concept, but people used different names. So consolidating the names were hard. And then just imagine you have a big motherboard. As I said, you take the heart of the motherboard out. You have a lot of these signals that are dangling in the air. There were too many signals. We needed to reduce the pin count. A concept to reduce the pin count, as you guys know, is time division multiplexing. So we used a concept of serial shifting the bits from one module to another module. CPLDs are necessary on both modules anyway for power sequencing, reset logic. CPU modules normally have CPLDs. For controlling the flash for the sake of security and such, CPLD is normally necessary on the secure control module. So we could just connect the two using few pins. For example, with 4 pins, a clock and a load and in and out, it's good enough to pass a lot of bits. So we use the serial shift chains to reduce the number of pins. Remapped a lot of pins that are not as critical into these serial shift chains. So there are different techniques here, register reads or multiplexing and demultiplexing, different techniques to map the signals into serial shift chains for different reasons. Sometimes you want to preserve the firmware that's running on the BMC to run the same regardless of which system it is running. For that, we use the mux and demux techniques. So this is a particular pin map implementation that we did for the POC stage. We're looking for feedback. It might change by the time we finalize the specification. So why did we do all this? The main concept is very good people are designing wonderful systems, and end users such as us, hyperscalers, would like to use them, but it takes a long time for us to put them into the data center because they don't necessarily meet all of our requirements. So it would be nice if an OEM, ODM building something can go into different data centers. It would be good for a data center provider, hyperscaler, to use not only one system, but many systems from multiple companies. By doing this secure control modules, we can accomplish both. I can give you an example. Yesterday, I was trying to describe this to some of my colleagues, and I just saw that somebody had a bottle. We can say that the bottle might represent the CPU and memory module, and the cap, this is a red cap, is the secure control module. Without our requirements, people can go and build a full system and then present it to different data center providers, different hyperscalers. But then hyperscalers might say, hey, I like everything about this, but this is red, and I'm a blue guy. Okay. You just go around, grab your secure control module, and plug it in. As long as the standards follow, sometimes it might just move it a little bit, but eventually works. It works in a short period of time. It gets readjusted a little bit, but in much shorter period of time than it would take to design the entire thing.
So is that the ultimate goal, basically?
No.
Everything except for a data center specific
Yes.
bit of information.
Right.
And then this secure control module is basically a data center specific plug.
Right. It is basically, that's why the name is DC, Datacenter-ready Secure Control Module. Now, it just happens that if somebody else already knows our requirements, it can already come with blue. And if we are all very, I don't know, maybe work together, we can make only one of these things and we'll work with different kinds of solutions. Well, let's just see if it works. It worked. So I could have one OEM or ODM build wonderful solution and can go to multiple blue, red, green data centers. Or the blue data center can choose to have solutions from different companies and enjoy it. Thank you.
Since we are compartmentalizing it, are there any performance implications?
Performance implications between the secure control module and the compute module. Performance in the form of doing diagnostics, doing RAS features, doing remote debug. You could encapsulate all those into a set of bits, set of firmware that comes with the secure control module. In that model, a company can work together with partners, build a particular set of firmware that you could call that the blue firmware. A different company might have red firmware. They might be exactly the same, but done in two different formats. One of the issues that we have is people do very good work. They do all the RAS features, but as they map sensor data into data structures, just as simple as the data structure comes in a different format, come from different companies, in the same data center, that by itself causes a lot of churn. We can eliminate those by just doing it once.
Yeah. You show that, for example, you're using the servos to protect the platform in terms of security. But when you do platform level secure module, is there any relation to the system level root of trust, any assumption that the SCM acts as a system level root of trust, or you support system level root of trust would be anything?
Well, in this model, Cerberus, as a root of trust chip, has a particular job. Its job is to protect firmware. There are different chains of trust that eventually get built on this, that will be done by software stack at different levels. As I showed at the beginning, we have, this is an out-of-band management technique. The data plane control will be totally separate. That's a different module. And on the data plane part, security encryption will, and key management will get done on its own.
Yeah, I'm more interested in the platform level root of
Right.
trust.
So on this side, the premise is that we start the first bits protected by a security chip such as Cerberus or others, and then we build the chain off of that.
How is aligned with RAM BMC? There was a standard on last meeting in Santa Clara, in San Jose, actually. There was a presentation about RAM BMC
Right.
and the standards and signals. So I saw some of the signals are different. The Pinout is different. So
That's right. Run BMC is another project that's being run. It is targeting standardization on Pinout for different BMCs. That was a very good start. It covered what one BMC, what the BMC itself needs. But at a system level, we saw in addition to BMC, we needed other things. Security was another aspect of it. Doing that one through supply chain was another aspect. So compared to Run BMC, this system is using potentially a cable-connected module. For that, we needed to reduce the number of pins. So we couldn't just start with as many pins as Run BMC defines. So we just had to cut it down. To cut it down, we had to go through architectural reasons to have these signals and judge which signals needed to be dedicated and which signals could be loaded onto shift chains. Through that, we had to change the pinout. So pinout is not the same.
And the root of trust is on the module or the platform? Like I said, do you want to put on the module or on the board?
It is on the module. The boards don't, by this definition, by modular building block architecture, individual modules do not have any bits on them. They're telling me we're running out of time. Thank you very much.